All right, so let's continue our talk about multi-layer perceptrons. The last thing I think that we were working on was this slide here, where we talked actually about multi-layer perceptrons, where we had started with a single perceptron node. We went to 2 in parallel, okay, and then we added the output node. So these nodes here are what we call hidden nodes. Some people even talk about these as being the input nodes. And so in that way, if you think about these as the input nodes, this as the output node, or nodes in other cases, then the hidden nodes are in between them. You don't see them. You know, you put in values at the inputs, you see the inputs, you get values out at the outputs, and then these ones are the hidden ones that are inside the so-called black box of your neural network. And actually, I'm not going to talk about this, but you can have multiple layers of hidden nodes, so you can have more than one layer that's hidden in there. So in the end, what we had here was the output being going through both of the 2 layers. Here is where it's going through the first layer, where I'm multiplying by the inputs by the weights, going through that activation function, and then the second layer is multiplying the outputs of the hidden nodes by the U matrix, and then taking the output activation function to get your output. Now, most people are not going to ever write an equation like this for the neural network output. I'm not sure why. I like doing that because it emphasizes to me that that black box that everyone talks about is an explicit function. You know, you put in a value at the input, there's an explicit function, there's an equation. You can write the equation, it's very long and it's very complicated, but there is an explicit equation that when you give it an input, it will tell you what the outputs are. So in that sense, there's nothing magical or mystical about a neural network. It is just simply an equation. And you can do whatever you want with that equation. You can take derivatives, and to do the gradient descent. You can do whatever there is with an equation. And sometimes people lose sight of that. So I personally like writing, an equation that represents what the output is as a function of the inputs. Understanding that it's the W and the U, it's the values in W and U that are our tunable parameters, what we call tunable parameters. We're trying to optimize, trying to find the best combination of all of these parameters. And so our matrix for our weights has become a matrix now, again, where the first index, which row it is talking about the input number, and the column is saying which node number. So the first row here, that is going to have to do with the first input, which is the bias. And this row is for the actual X. And then this column is for the first node, and this column is for the second node. All right, so we had the learning rule. We have to update the W's depending on the gradient of the error with respect to W. That is, how much does the error change when I change W? And I want to go in the negative direction where E decreases rather than where E increases. And we do the same thing for U. Okay, so we had some code before that did the gradient descent for just a single node. And it gets a little bit more wordy here, but it's really the same idea, okay? That I'm going to have a symbolic expression for each one. I'm going to have a symbolic and a numerical expression for each of the 4 values of the W weights, each of the 3 U's, okay? And so they're going to both exist as symbolic things, and they're going to exist as numerical things. The error really looks the same. I just have to multiply by each of the pieces, and you just follow through, update each one of the weights, update each one of the U's. It's the same concept, okay? Again, in the code is this as an example, but it is so inefficient because it runs so slowly. Okay, so what I had to do is, I think it took an hour or two to make this video, so I screen captured as it was training this neural network. And let's see, will it run? How do I gotta get it off that laser pointer, I think. There. So this is what's happening during the training process, and I'll play it again a couple times for you, but you can see as it learns, it adjusts the output. The blue is the actual output of the neural network, and you can see it's adjusting the output of the neural network as it gets better and better and better as it moves on. Okay, like I said, this took an hour or two, and you see there was something big happen. All of a sudden something changed really quickly. It happened to get in one of the steeper parts of that error surface, and suddenly something happened. Okay, sometimes things go fast, sometimes things go slowly. And so now here's, I'm not sure if it's quite done yet, but anyway, it's pretty much there. And so the blue is the output of the neural network. And you can see that's not so bad. I mean, we have two nodes that are both sigmoids, okay, that they start at a large value and then they swoop down to the low value. Okay, and the weights on those, the output with the U's, okay, what the U can do is it scales it. You multiply that output by some scaling factor, okay, which could be positive or negative. So if it's negative, it'll make it be between 0, rather than being between 0 and 1, it'll make it between 0 and -1. And then the scaling factor can make it taller. So now that's how we've gotten away from only being between 0 and 1, because the output weight can scale it. Okay? Then the bias in there can shift it side to side as well. And so we can shift where it is, we can shift how tall it is, and we can shift whether it's oriented up or it's oriented down. But it's still going to look like a sigmoid. And so here you can see we've got two sigmoids. Here's one of the sigmoids, and here's the other sigmoid. And that's the best that we can do with two sigmoids. Now, you can imagine if we were to have lots and lots of these things, that we could have, one sigmoid play a role here, another sigmoid play a role here, and another here, and here, and here, and here. And so, that's actually, you can actually prove, there's a theorem, it's a classic neural network theorem that proves that that as long as you have enough nodes, you can represent any function to an arbitrarily small error with infinite many of these nodes. I mean, you can start imagining if I put in 4 or 5 or 6, I can get more and more. Yes?
Maybe akin to the splitting, I guess, that we did, where it had cubic functions or quadratic functions and just made them over from point to point.
Right. So like a spline. So if you have a regular regression, you have one polynomial. And you can't represent all of the points in that regression exactly. But in a spline, every set of 2 points has its own polynomial function that can make it exactly go through those 2 points. Then I have another polynomial function, so every 2 points has their own polynomial function, and I can exactly represent those points. So yes, this is very similar in a way that if I have lots and lots of these sigmoids, I can make them represent it very well, at least to an arbitrarily small error. Yes, that's a good analogy. I like that. Hadn't thought about that one, but absolutely, that's a good one. Okay, so the blue here is an addition. It's a sum of the output of each of the output of this piece and the output of this piece, and that's what the cyan and the green ones are those two nodal outputs. And you can see they both go to 0, and they can be bigger. They've gotten a scaling here, so they can be bigger than it, and they can be shifted. But this piece right here, this guy here, is what can shift where they are up and down.
Your mouse pointer's not showing up.
Good point. Thank you. So, we've got these going from 0 to a scaled value, 0 to a negative scaled value. So you can see, if we were to look at the weights, one of the weights would be negative and one of them would be positive. Okay, and so they're still starting here at 0, but when I add them together, I'm getting something that has, gets to this blue one. So let me go ahead and let me replay this. So you can see from the beginning, they all start at basically nothing, and the two nodes are adjusting to where their values are and what they have, and adding together, they're giving this blue thing that gets bigger and bigger. You see the green one keeps getting pressed farther and farther down. It's getting a larger and larger weight to extend it down, which is bringing the blue part down as well. So here, at least with two nodes, we can see during the training process that it's trying to do the best it can with two sigmoids to be able to represent this parabola. Okay? All right. Let me not forget to have my laser pointer. So this network here is pretty simple. It has one output, technically two because we're adding the one for the bias. It has one output, it has two hidden nodes, and it has one output node. This is about like almost the simplest network you can get, and you look at the diagram there and it's pretty dang complicated. So one of the things we'll do is we'll sort of compact these diagrams around by sort of identifying the parts that are for one, what we call a node or a neuron, that is derived from this idea of what's going on in our head. Okay, and so we say the weights that are associated with each of the inputs. So what the lines that are crossing into here are the inputs into this node, and then each one of those inputs has a particular weight. They get summed together, and they have their transfer function applied to it, and then there's an output. So that this thing here is considered one node where it has a certain number of inputs and one output. And those things are what we're going to block together. So this little circle here represents all the things that are inside of here: the weight, the sum, and the transfer function. And so each one of these nodes has its weights. Each one of the two inputs coming in here have a weight and the sum and the transfer function. And when I eventually get to talking about the biological neural network, it has a very similar structure in what we call one neuron in our brain. Okay, so when we look at here, we can see there are two hidden nodes in this network. There's one output node in this network, and there's one true input if we're talking about the biases. Oftentimes, the biases are not going to show up. They're just sort of, we added them in there so that the matrix multiplication would be convenient. So almost never will you ever even see those biases written there. Okay? So that's even simpler. Here's my one input, it's a scalar x. I've got two hidden nodes, I got one output, and that's the output of the neural network. Okay? So each of these nodes in one of those circles, it outputs its activation function evaluated at a biased linear combination of the inputs. So we got our inputs coming in, they're at a linear combination, each of them is multiplied by something and they're added together. And then there's a bias in there. There's the offset, the intercept part. Okay? Now, of course, in Scikit-Learn, you don't have to do all that stuff, and you don't have to wait an hour for inefficient code to run to get your output. You've got, you need to import the multi-layer perceptron regressor. There's an MLP classifier as well. Okay, and basically what that depends on is what the output transfer function is, and I'll talk a little bit about that soon. So we need to import the MLP regressor. I rename it as MLP just so I don't have to write so much. And then of course we've got NumPy and we got Matplotlib. I go ahead and define the number of hidden nodes as being 2. I've got a dense values of x so that I'm evaluating not just at the data points for the training but in the middle so that I get a nice smooth curve. These are my training points, x and y. This is just the x squared minus x plus 4. So that's the polynomial that it has there. And then here's the thing. I'm going ahead and I'm going to instantiate, have an instance of the class, the MLP class, and I'm calling its constructor. And I need to say, what are the sizes of the hidden layers? I want a single hidden layer with h nodes in it. So I'm passing to it a tuple with one value in it. If I had put something after the comma, that would be the second layer. But if I only want one layer, I have to send a single tuple. And you remember we talked about this in the class before, where if I just did parenthesis h, that would just be order of operations parentheses and not tuple parentheses. I have to put h comma to make it understand that I want to make it a single tuple with one dimension. I need to tell it what the activation function is for the hidden layers. Okay? And so I'm using the logistic sigmoid function. There's plenty of others. There's tansig, which is the tangential sigmoid function. There's relus and all these others that we'll talk about that have become more common. The sigmoid is sort of the classic, the original transfer function, and interestingly enough, it's kind of fallen out of favor in the machine learning community. It's kind of becoming a dinosaur, but for people like me that have been working for this for a long time, sigmoid's my go-to. But we'll talk about that more in the next project. Then we have to talk about what the solver is, and this is essentially what is the optimization algorithm, what is the learning rule. And I gave you the learning rule that is pure gradient descent, and I talked about there's all sorts of other different learning rules. This LBFGS, it's sort of a variation on the gradient descent. It doesn't always go straight downhill. It has some other things involved in there, but it's essentially the same idea. Now, there are other ones like stochastic gradient descent, and the most popular apparently nowadays is this Adam one, and we'll talk again more about that when we get into the deep learning, the deep learning stuff that has come about in the last five or so years. That's sort of changed a lot of the way we look at some things. But that's sort of the classic one, is the LBFGS and the logistic. Now, what I find really curious is that there is a learning rate input into the neural network, and that's the mu. Let me go back. That's this guy here, this mu. That's what we call the learning rate, and that says how big of steps do we take. But oddly enough, the learning rate, at least in the documentation for Scikit-Learn, says it's not used for the LBFGS training algorithm, which confuses me. It only works for the Adam one. So I don't know, that's a little weird, because, and if I have some time at the end of today, I can do some messing around with some of the parameters, and you can see that if you choose a learning rate that's too high, you get sort of instability. You jump, you may not be going down the hill, you might jump to the other side of the hill if you have a learning rate that's too big. So that's one thing to keep in mind. Apparently, for whatever reason, that is not something that we can change for the LBFGS. Then we use MLP. We do ANN fit. Surprise, surprise. Okay. Then we go ahead and I go ahead and predict. Surprise, surprise, on the dense axis. And then I plot the x denses versus the predicted y's from the neural network. And that's what we get with the blue curve. And that's with 2 hidden nodes. And here's with 5 hidden nodes. There we go. That's pretty darn good. It's a good result. So, back when we first started doing things simple and it was like crap and it was terrible, and now finally we've gotten to a point where at least with 5 nodes we're getting a pretty good job of representing this parabola. Of course, polyfit would be better because it's a parabola, but who cares? We're going to eventually look at much harder problems that a polynomial fit would not work for. So, our general structure here, we have 2 nodes, a single scalar input, 2 nodes, and 1 output. A single scalar input, 5 hidden nodes, a single output. Now, in general, we're going to look at things that look something like this, where there could be n number of input features to our neural network, h number of hidden nodes, and we might have multiple outputs even, which in this problem we are in the end, we're going to talk about having 2 outputs rather than 1 for the angle, so that we can handle some periodicity issues. Okay, so in general, I'm going to have n number of input features, h number of hidden nodes, and m number of output labels. And we need to be able to handle, in terms of the linear algebra and all that stuff, all of these different situations. So our W, at least, there is going to be a U vector, a U matrix as well, but just I'm going to look at the W vector, and it pretty much you can draw an analogy of what happens with the U one. But again, this W, the first index is the feature number, and the first index is the feature number, the second number is the node number. Okay? And our X now is not just 1 and my X, but there might be there's n different features in here. So this row vector has become quite large depending on how many input features you have. And then our matrix multiplication all works out nicely when I do X times W, and then I take my activation function of that, etc., and move on. Okay, now, most of the time we're going to be dealing with more than one sample. I want to train my neural network on more than one value. I mean, I did. I mean, with those, there were 10 values, there were 10 magenta points, and I needed to train that on those 10 points. So, how do we represent that? We make X into being a matrix rather than a row vector, where every row represents one sample and every column represents one feature. Now that's also a recurring theme here. Now, as it turns out, the very first column are all filled with ones for the biases, and then it's all the rest of them that are actually the features, and they're representing my entire data set now with X as a matrix. And the way the matrix multiplication works out, you know, this is the first node because columns are in a node. So this represents the first node up here. And so I take these things and multiply them by these things, basically dot product of this vector in the first row with this vector in the first column, dot producting them together, multiplying them, adding them all together, and that gives me the sum of the value in this node that then goes to the activation function f before moving on to the output layer. So all the matrix operations work out just the way we want them to. Okay? Now, if we look at what is the relationship between all of these things, the N's and the H's and the M's, and how it works out in the Scikit-learn. As I was saying, by choosing MLP regressor, that is selecting essentially what the output function, the output transfer function is. And I haven't been able to find in the documentation, but I think it's just simply the identity function. That it just, whatever the output is, it just takes it. If we had a classification problem, it would probably apply a sigmoid there so that it forces the value to be between 0 and 1. Is it that class or is it not that class? Okay? So by choosing what type of multi-layer perceptron in Scikit-learn, that's selecting what G is. Then, one of the interesting things you'll find is when you try to do this, the ANN.fit, okay, it's expecting, now right now I'm dealing with this, there's only a single input, so there's only one input column because there's one feature and lots of samples. So there's lots of samples, but there's only one input feature. And you'll see when I did this, I reshaped it. Because if I do np.linspace, numpy linspace, it will give me a 1D array of values. And then if I try to pass a 1D array of values to fit, it will be confused. Because it'll say, well, is this lots of features in one sample? Or is this lots of samples in one feature because I passed it a 1D array? So actually, I think it throws an error if you try to pass it a 1D array.
Support vector machines did the same thing.
Okay. Okay, so you're already familiar with that problem. Okay. I should have explained that to you guys earlier. But at least the error message is very kind because it says use the reshape -1, 1 to make it the right.
It tells you which one is for
Right. I mean, when have you ever seen an error message that was that friendly? It doesn't happen very often, does it? Okay? Now, what's interesting is that in the Y values, if you pass it a 1D array, it gives you a warning and not an error. Because with that, I guess because it knows from the X that I have lots of samples, it knows that it has to represent the Y's as lots of samples and not many outputs. So it must be able to do that logic itself, with the error checking internally. But it does throw a warning. So I've used the ravel command to pull them all out into one long thing, and it turns it into a 2D array. Okay, so I've done that just so that I don't get the warning. As I said, the logistic, that's what the activation function is for f. The h there is the number of hidden nodes, okay, and then the solver as well. Okay. Now, here is another example, a 3 output example. So what and a 2 input. So this problem has an xy as the input space, and I want this neural network to learn 3 different 2D functions with 2D inputs. So I want it to learn, what is it, cosine, sine of x times y. I want it to learn the exponential of x minus y, and I want it to learn the constant function 1. So I want this to learn 3 2-input problems, 3 3-dimensional problems. So I'm going to have 3 outputs. So one of the outputs is supposed to output sine of x times y. Another output is supposed to do exp of x minus y. Another is just supposed to always output 1 no matter what. So I have 3 outputs, and I have 2 inputs for x and y. And I want to train a single neural network to solve all 3 of these problems simultaneously. So this is my way of giving a more general example where I have multiple inputs and multiple outputs. Now, actually making this work is a little complicated, because if I want to plot them, I have to have a mesh grid. So I define my x and my y's here as a mesh grid, okay? And remember, that gives a matrix for x and a matrix for y. And that's just so that I can plot them with the surface plot. And then I go ahead and calculate what the z is for all of those things, all of those x's and y's. And then I'm going to put those, that's a matrix now, right? Yeah, z, that's going to be a matrix. So z is going to be a matrix, and I'm putting that in a list. And then I'm appending to that list the next matrix, and then I append to that list the next matrix. So now I have z as a list of 3 matrix, 2D arrays. I really shouldn't call them matrices, because NumPy matrix is different. So it's a list of 3 2D NumPy arrays. So then, the features, they can't be organized. I've got this x 2D array and this y 2D array. That's not the way the features need to be represented for the fit. So what I do is I take that 2D array for x and I reshape it into one giant long column. And then I take the y 2D array, reshape that into one giant long column. And then I column stack those 2 things next to each other, so that now I have 2 feature values. The first column is x, the second column is y. Every row is one of the samples. And there's going to be 50 times 50 samples, because I use the default linspace, which will give 50. So there's going to be 2,500 rows and 2 columns in feet. Then I need to build my labels. Okay, those are, I'm going to fit the features versus the labels. And again, I need to draw out the z's. That z 2D array, I'm going to reshape it into one big long column. Z, that's Z1, Z0. Then I take the Z1 2D array, reshape that into one big long column, take the Z2 2D array, reshape it into one big long column, column stack those 3 things together, and now I have my labels that has 2,500 rows and 3 columns, one for each of the 3 z's that I want. Okay, and then I'm going to go ahead and define my multi-layer perceptron. I'm going to have a single hidden layer with 4 hidden nodes, and then I'm going to fit my features to my labels. Then I go ahead and do a predict, okay? And that predict is going to return a matrix, where every row is the prediction for that sample, and each column is the output, either the first, second, or third output. And so then I'm going to take the first output here in the 0th column, all of the rows. I'm going to reshape it back into 50 by 50 so that I can do a surface plot. And I'm going to do the same thing. I'm going to reshape the 1 index and reshape the 2 index, put them in 3 different variables. I'm going to make my figure, and I'm going to do a subplot with 3 rows and 2 columns. And I go through there, I'm going to plot the actual stuff in the first column, that's the ground truth values, and then the predictions in the second column. And you can say, I mean, it doesn't do an awesome job. It's only got 4 hidden nodes, but it does a reasonably good job, at least, of getting within the ballpark. Okay? So this is a more general case, multiple inputs, multiple outputs. Now, you'll see I had a bunch of print statements down here to do the shapes of some of these 2D arrays. So the feature shape is 2,500 rows in 2 columns. X in one column, Y in another column. 50 by 50 for the 2,500 rows. Okay? My label matrix, same number of samples, but 3 outputs. Then, the rest of these are pulling out data members from the neural network. Okay? So I'm doing ann.coefs underscore. I don't know, they love underscores. I don't understand that. Why do you put an underscore at the end of a variable name? I don't know. It's kind of a standard that's if it's a data member in Python, you put an underscore at the end of the name. I don't know, I don't get it, but whatever. So, coefs is essentially the weight matrices. Okay, the weights. And it's a list. There's going to be a list of them. The 0th L1 is going to be the W's. This is going to be the W's. And the coefs 1, those are going to be the U's. Now, the way Scikit-Learn has organized this is in a matrix where the biases aren't at the top of the matrix. Where do I go to show you that? These guys here, all of these are the ones that are multiplied by 1, right? Okay, these are all that gets multiplied by that. These are the ones that get multiplied by the 1s. Okay, the first row is the feature number, and the first row are the 1s. Now, Scikit-Learn has not, they differentiate between the weights for the biases and the weights for the actual inputs. Okay, so what they have here as intercepts, those are the weights on the 1s. And the coefs are the weights on the actual inputs. Okay? And so you can see here that the layer weights, there are 2 inputs and there are 4 hidden nodes. So there's a total of 8 weights for each one of these nodes in each of the X and the Y. And then there are 4 biases in the hidden layer, in the layers, because there's 4 nodes. Okay? In the output, there's, this output layer here has 4 inputs and 3 outputs. So there are 4 inputs and 3 outputs in the layer weights, and there's 3 nodes, so there's 3 biases. And then, of course, the shape of the output of the neural network, the N that I got when I predicted, that's going to have the number of samples and then however many number of outputs there are. Okay? So there's 50 by 50, 25 rows in the lin space. 50 by 50, 2,500 rows in the lin space. Yes?
50 just remember that lin space there's in this.
That's the default. The default is 50. In MATLAB, lin space has a default of 100. So for whatever reason, NumPy decided they wanted to change that default. So that's just the default. If you put a third argument there, 0, np.pi divided by 2, 100, then it would be 100. Then, this has 2 columns. I stack together 2 columns. That's where the feature matrix gets its 2 columns. I stack together 3 columns to get the label matrix to have 3 things. Okay, there are 4 nodes because I defined that in my constructor for the MLP. And then, interestingly enough, nowhere have I told the neural network how many outputs there are. But it infers the number of outputs depending on what you pass as labels. as labels. The labels I pass, there's 3 columns, so it knows, oh, I have to have 3 outputs. So I'm fitting this thing to have 3 outputs, which is a little weird that you don't say when you do the constructor what the number of outputs is. It infers that from the labels that you pass to it. Okay. All right. So let's summarize this whole process of the neural network, how we're training it, and all of that with this example, the 2 input and the 3 output example. This is the equation for the neural network output, and we know at least in this particular case we have these different sizes. Okay, so the first thing I need to do is I need to multiply the input matrix X, which has all of the samples in it, and at least the way I've represented it has the first column being all the ones for the biases. And then I need to multiply it by the weight matrix. Okay? And so these guys right here are the 2 columns in the 2500 features. And I'm multiplying that by the weight matrix. And the way that Scikit-learn represents that is the first row here are the layer biases. There's 4 of them. And then the layer weights are the 2 nodes and the 4 inputs. No, 2 inputs and 4 nodes. I had that backwards. Okay? Then we multiply those things together to get, and they multiply and sum to get me the sums for each one of the nodes. And just for simplicity, I went ahead and labeled these alpha, beta, gamma, and epsilon for the 4 nodes. And so I'm going to have an alpha, beta, gamma, and epsilon value for each one of the 2500 input points, samples. All right? So there, for each one of the x and y pairs, there's going to be a different alpha, beta, gamma, and epsilon, and they're going to fill this matrix that is the x times the w. And then I need to take the function, in this case a sigmoid. I'm going to take the sigmoid element-wise of each one of the things inside that. So I'm going to take my sigmoid function of each one of those pieces. I'm going to horizontally stack that with a bunch of 1s, and then I'm going to multiply by my output weights, where my output weights have a certain, the first row of them is the biases. That's what we get with intercepts 1, the second one in that list. And then the coefs 1 is the stuff that's in the bottom part of here. I have 4 inputs to this output layer, and the output layer has 3 outputs because there's 3 nodes. Okay? Now, that gives us our outputs. And we have 2,500 outputs, 1 for each sample, but there's 3 of them for each one of them. And that's what we get to 2,500 by 3. So this process, again, it's an explicit function here. I take my inputs x, I put them in, I go through this whole process, do all these calculations, and out pops my n. Okay? And this is what we call the forward pass, or forward propagation through the network, where I take my inputs and it will give me what my predictions are. Then I take those predictions and I compare them with the ground truth labels. And you'll notice here that these matrices are no coincidence the same size. The label matrix has 2,500 rows, 3 columns. The output has 2,500 rows and 3 columns. And we get the error by subtracting, element-wise subtracting each one of those pieces. And then those errors, I then find how sensitive are those errors to changing all of the weights, including the biases at the layer level, and all of the weights, including the biases at the output layer. So that error then helps me to decide how do I change the U's and the W's. And this is what we call the backward propagation. Okay? And so we go forward to get what the outputs are, then we use that information and go backward to change the weights and update them and make them better. So that's why a lot of times they'll talk about backprop nets, back propagation nets, where we take the error from the output and use that to help us update things. Okay? So that brings us sort of closure for all the stuff on the artificial neural networks. And now we can think about, where did all of this come from? I have developed this all from a mathematical perspective, kind of started off with a regression idea and built all the way here. But the ideas that led people to come up with these mathematical constructs come from the biology of neurons. And in our brain, we've got these neurons, and each one of them they're cells in our brains, and they have a cell center, cell nucleus, that's called the soma. Okay? And then each one of these neurons is connected to many other neurons. And so essentially what happens is any neuron is connected to all these others around it, and the neurons around it are either sending it pulses or not sending it pulses. It's basically a binary system. Either it's sending a signal or it's not sending a signal. And then that node that's getting all these signals from the other, it takes all of them in, and it basically says, if I get enough pulses from the people around me, I'm going to send a pulse myself to all the ones that I'm connected to. So the node here has connections. In this case, it's drawn to have 3 connections to other nodes, where these are the pieces, these are the outputs of other nodes. And where the other node's output is connected to this node's input is called a synapse. And the synapse is basically a connection between the two. And when they talk, you hear about saying that, oh, well, doing this activity strengthens connections in the brain. Okay? They're talking about the synapse. That it's essentially the weight, how much, if that signal comes down the path, how much does that contribute to me firing my neuron? And so the stronger the connection between the nodes, essentially the higher the weight is for that signal coming down coming across that synapse. So the weights are saying, how good of a connection is there? How strong is that connection? And it basically amplifies the signal as it's coming through. And so we've got the synapse here for this node that's modifying the signals that come in. So all of these 3 signals come in, they're collected at the soma, and if they are strong, if the total of those synapse values that it gets in are big enough, it will send a pulse down its output. And then its output is connected to other nodes around it, and that will contribute to whether the other nodes around it fire. Okay? So one neuron is considered here to be the soma, and these so-called dendrites, the dendrites are what accept signals across the synapse. So the dendrites and the soma, and then the axon is where the output goes and is connected to the other pieces. So the axon and the soma and the dendrites all form what are considered one neuron. And it has a very close parallel to the artificial neurons that we talk about. We look at the different inputs, x1, x2, x3, coming into this neuron, and then the synapse is representing the weights. So each one of the inputs that's coming in is multiplied by a weight. If it is a strong connection or if it's not a strong connection, then they're all summed together. Then that value comes down the dendrite into the soma, where they're summed together. And if that value is greater than some particular threshold, which is essentially our bias, if that thing exceeds that threshold, then we're going to output something. So the activation function is either I send a pulse or I don't send a pulse. And so essentially, if this value plus the threshold is above 0, then it fires. So essentially, if let's say that threshold is 5, okay, and so if I have something that is, if the sum of here is -5 or less, it won't fire. If it's -5 or higher, it does fire. And so basically, this thing here is saying, at what level do I need in order for this thing to fire? And it's a binary decision. Either I'm sending a pulse or I'm not sending a pulse. And that's essentially how it works in the brain. Okay, we don't have different strengths of the signals. It's either it's sending or it's not. Okay, so this is the idea, and then that output goes out the axon, and that's the output. Okay, so the idea of the sigmoid, the original sigmoid, like I say, that's fallen out of favor, it does that. Either it's 0 at a small value, or it's 1 at a large value. This 0 to 1, that's a step function. And I can't do a step function. I can't do gradient descent on a step function because it doesn't have a kind derivative. Okay? And so the sigmoid is basically a way of making this tractable in a mathematical sense. It still models the idea of I send or I don't send, but it's differentiable. Okay? So, if we compare biological and these artificial neural networks, okay, the biological networks are parallel, and the artificial are serial. Now, if Tim were here, he'd be like, but I parallelized my stuff. And I'm like, yes, you did, but that's not the same thing. What you're parallelizing is looking at all of the different inputs. You're doing many inputs at the same time. Or what you're calculating at the node level is being done in parallel. But what happens here is that all of the signals are being sent at exactly the same time, and all of the neurons are processing at exactly the same time. Okay? In our neural network, first we have to calculate x times w, and once we get that, then we can go ahead and do the u times the f's of that. We're not doing those two things at the same time. We have to propagate forward through the network and then propagate backward. That is done in serial. What's done in parallel is that I can do that for many inputs at the same time. So we may be able to parallelize our inputs. They're parallelizing all of the nodes happening all at the same time. Now, there are hardware structures that are intentionally made to happen in parallel. So there are, neural network computers built specifically only for that, and that they can do some of these things in parallel, but it's not really very common. The vast majority of the artificial neural networks, they are really done in series. And we do a little bit of parallel stuff to speed up the computation that otherwise would be in series, but it's not truly parallel where all the things are firing at the same time and all activating at the same time.
You said they're not common. Is that mostly due to cost or just uses are lower?
I'm not sure why they're not common. I don't know. I've never really been in that research in that. I know they exist. My gut instinct is that they haven't given any better performance than having a high-performing computer working in series with a GPU to speed up things. That's my guess. And this is one of the big mysteries, because you look at that's what's going on in the brain that, at least to me, I think is what we're missing, is that there's something happening with that parallelism or something that we're just not getting right, and that's one of the reasons why we're not doing brain-like things. Because if you look at the switching speed, those signals being sent in the brain are only going on about the kilohertz speed, where on a computer we got gigahertz. We're like, well, we're thousands of times better, faster on a computer. How come we're not doing things better than what's in the brain? And I think it's coming down to that parallel stuff. The other thing, too, is the number of neurons. In our brains, we have as many as 100 billion neurons in there. And, nowadays, with deep neural networks, I had to change this number. I had to change because previously you really didn't ever work with more than 100 or a couple hundred. If you had like 300 nodes in your network, that was like a giant network. Okay? And that's not, nowadays we have thousands and thousands of neurons in these networks, but we're nowhere near 100 billion. Okay? And I suppose another comparison I should make here is that most of the neural networks, now there are some recurrent networks and other things, most of the networks, it's feed forward. That you go from this node to this layer of nodes to this layer of nodes to the outputs. Whereas in your brain, everything's all jumbled together and there's stuff connected everywhere in all sorts of different places, and actually the connections of which nodes things are connected to change over time in our brain. So that's another big difference, is that we don't have this nice neat layer structure in our actual brains. And so there's a lot of people doing research on the biological inspirations for getting a neural network. The type that I've shown you here, really, our brains don't look anything like that. It's so much simpler than that. But there's plenty of people that are working on trying to build artificial neural systems that look more like what's in the brain. And they just don't know enough about the brain to be able to get them to be much better. So, that's something to keep in mind. So that's good. We're all the way to 1050. So I do want to do messing around with some of these values with the hidden node levels and some things. We'll test around with some things next time. And I guess next time we'll also talk about early stopping and some of the practical things about training these neural networks. All right?
Just cutting it short, I guess, or setting a threshold like, okay, this is good enough performance. Or...
Right. So, when you do performance, we also need to be careful about things like overfitting, where it learns only this data set and does not learn other data sets. So there's lots of practical details, and that's, again, where the critics of neural networks are like, yeah, they're great and all, but you got to be pretty smart and have a lot of experience in neural networks to be able to train one to do what you want. So there's a lot of the so-called hyperparameter choices. How many nodes do I have? How do I set the initial weights, the initial random weights? How does that affect the results? There's a lot of things to think about, and I'll show you those next time.